Gesundheit. My apologies for the technical difficulty delay, but now I've got the camera working again. Chapter 9, sections 1 and 2. What questions do you have for me? Okie dokie. Going to be a short day otherwise.
9.1 can be C. A little bit how to find out where it's decreasing.
Okay, so you're given an expression for the derivative, right?
Yeah.
I want to know where a derivative is increasing. I'm sorry, where v is increasing. How does a derivative tell me that? Exactly. It's increasing when it's positive, decreasing when negative. And didn't the first part ask me to figure out where it was 0? So really all you have to do is make a sign chart. The problem is you don't have any numbers, right? It means I have to do everything in terms of the number a. So I could do things like take a over 2 or a over 4 or a 2a or something like that, and that will put me on either side of a. Make sense? Now, interestingly enough, this particular model, I didn't choose this problem at random. I know it sounds like I should. There is, the idea is when you stimulate a neuron, the electricity goes off, that nerve is stimulated, and then it stops. But if there is no stop, if there's no relaxation effect, the nerve stays on, right? I have a question for you all. Are you aware of the weight of your shirt on your shoulders? Not until I said something, right? But it's been on there all morning. You haven't felt it. Even though your body knows your skin is being touched, you just tune it out. The absence of relaxation effects allows the nerve electricity to adapt. I wish I was making this up. One of my graduate student buddies back in 1990, whatever, was studying exactly this effect on mice. And he wanted to know how far apart the stimuli had to be to prevent or to cause relaxation effect. If they were too close together, when would it stay stimulated? And so they were measuring the neural response to pulling a rat whisker. Seriously. He put wires into the brain to the centers of the brain that measured neural sensitivity of the whiskers, and then they held the rat's head in place and tugged the whisker a couple of milliseconds apart. And then they made the times get closer and closer together, and they would measure the neural reaction until instead of having 2 peaks, they got sort of one combined thing, and then they got 1 peak, and then it started to get lower as they got closer together because there was no relaxation. So one day, out of pure curiosity, I asked Dave, how do you hold the mouse's head still? And he said, well, first you take a 10-penny nail, and everybody in the room kind of went, what? And you glue it upside down to the top of the mouse's head so it looks like a little unicorn. And then you clamp the nail in place. And thus you have little unicorn mice wandering around the lab. So I picked this problem in honor of Dave Pinto. He was working in Dr. Ermentrout's lab at the University of Pittsburgh in cognitive neurobiology, which is at this point a $2-point-something million lab. Anyhow, never know where calculus is going to show up. More questions? Little white lab mice with unicorn horns. It was silly. Oh, no, dissolvable glue. They could take the nails off the mice. That was the weirdest part of this was actually watching the lab setup, because the mouse is not medicated; it's just held in place, so it's restrained in its body, and its head is held in place so that the whiskers can be tugged with precise measurements. They actually had a little clamp hooked up in a little gear, and it would pull with particular force. They didn't yank the whisker or anything like that. Animal experiments are very weird.
They had a nail on the head. How did they measure how did they measure the response?
Wires coming in from the side. First, you have to wire the mouse brain. Then you hook it to the computer. It wasn't like the Matrix. You couldn't just jack the mice in. Yes, ma'am. 27. So this is our same circuit, but instead of a load, we have a capacitor. Electromotive force, capacitor, resistor, switch. Capacitor is measured in farads after Michael Faraday. Resistor in ohms. Battery in volts. And this time we're told Kirchhoff's law, combined with Ohm's law, tells us that resistance times the change in charge on the capacitor plus 1 over capacitance times the charge is the electromotive force. I want to cheat and do the same thing we did last time. Get the Q dt alone. Then I'll plot this, only it'll be Q in this direction instead of I, and T in this direction. So that's our Y, that's our X. And so when it says to draw a direction field, I need to get this set up with the numbers they've given me, right? 60 volts, and this time it's 5 ohms and 0.05 farads. Make sense? Yeah. So that's our derivative. I want the derivative alone. I want everything else on the other side, like I had I prime alone in the one I did in class. Same exact setup. And because there's no t anywhere in this equation explicitly, this is again going to be an autonomous picture. The lines should have the same slope, whether they're positive or negative, as we go from left to right. They should only change as we go up or down. You have this circuit. Anytime something blinks, because a capacitor acts like a jump point. All the electricity comes from the battery, builds up on one plate until the static is strong enough that it jumps across to the other plate. And usually there's some medium in between these two called a dielectric. And air has a dielectric of like 300,000 volts. So you got to build up a lot of charge before it jumps. So if you have a turn signal, you flick the lever, you flip the switch on, and your turn signal goes on, off, on, off, on, off. What it's doing is it's building up the charge till it jumps, then it goes through the light bulb. So instead of a resistor, that one has a load. The circuit is slightly different. That's exactly how an intermittent flasher works. Windshield wipers, same idea. Your camera flash works like this too.
I would say a limited value would be that one.
Okay, so we're going to have some equilibrium solution, right? somewhere, if this picture looks like the one from class yesterday, we should get something like this. This is the class example. And in that case, if I think of what happens when I start stuff, yeah, they all seem to have a limiting value, don't they? The limit as t goes off to infinity of q of t appears to be a constant. And I should be able to show that here as well. More questions? Yes, Leo. So in number 2, you're given a direction field. So all you need to do is draw on this picture. It says, sketch the graph of a solution given the condition y of 0 equals 1. So I want to go to the point 0, 1 and try and draw a curve that would go that way. Now at 0, 1, what do you think the tangent line is doing? So I should be going up. But then as t goes up, I'm going to curl back this way, aren't I? So somehow I should be coming down and hitting that. I might also be able to do it from this side, right? Come up and hit that. So there should be some sort of a curve that goes through that point. If y of 0 equals 0.2, I'll go through this spot. It might actually be to your benefit. It looks like you've got the picture for this on your computer. I'm sorry, I don't know what you mean by that. Oh, if delta x, y, so if you're going to graph this, it's delta x, y equals 1 tangent of pi y over 2. Because that's our equation in there, right? Y prime, so y prime goes here, the top is always 1. And that would allow you to make the picture in Grapher on your MacBook. Which, by the way, you could then just print out and write directly on if you want. You don't have to try and draw the curves in Grapher. You can sketch those by hand. Uh-huh. Then you would say, oh, this happens where y is equal to 1. Right? Because your limiting value is equilibrium solutions are in terms of y. The horizontal line. Horizontal lines where y equals a number. What number? You said ever needed. You could write out words if you wanted. You could write all multiples of 2. Leo, better? Yeah. Wonderful. More questions. Promise we actually do calculus with this next week.
18 on 9.2 as well.
9.2, number 18?
Yeah.
So this time we have a picture of the graph of f of y, right? And our equation is telling us about this side. Our differential equation is y prime equals all this stuff. And notice that is just in terms of y, right? There's no t over there. That means the direction field is going to be autonomous. So I'm going to cheat slightly. I'm going to make up a different picture. I literally just pulled this out of thin air. And what I want to draw is a direction field, right? So if I draw a direction field, then the y-axis is in that direction. Okay, wait a second. I know that the definition of an equilibrium is where y prime is 0. Right? But y prime is equal to this f of y. Where is y prime equal to 0? No. Y prime is equal to this. If I ask where y prime is 0, I'm asking where this is 0. Not where the derivative of this. That's the problem. Y prime and f prime are now different. Geeky bugger. So where is that graph? 0. And where else? So I know at a height of 0, at a height of 3, and at a height of -2, my slopes should be horizontal. Those are equilibrium solutions. Now, the best part is everything else goes back to the first question you asked me about V of t. I want to know where the arrows are going up, where the arrows are going down, right? And that's told to me by the derivative. When the derivative is positive, we're going up. When the derivative is negative, we're going down. This graph is the graph of my derivative. Where this is negative, I'm going down. Where this is positive, I'm going up. So down here, in y values that are less than -2, is this positive or negative? Because we're down here, right? And those y values are negative. So that means that, and they start out really just barely negative, and they get more and more negative. So I would expect arrows that are a little down and then down, right? Now what about between -2 and 0? But it starts out a little positive, gets more positive, and gets less positive, right? So I would think they would be a little up and then more up, but then they're less up, right? A little slope, a big slope, then a little slope, but they're still all positive. How about between 0 and 3? Little negative, more negative, less negative. Above 3. But a little positive and then getting more positive, right? Now, this is autonomous. So even though I only drew the arrows in the middle, they should have the same slope no matter how far left or how far right I go on the same height. I freely admit to being a crappy artist, people. With me so far? Okay. Now, I've got two different kinds of behavior as we go from left to right in this picture. Pick a starting point. A y value. Okay, so if I start at -1, then I should be going up. And then I moved over a little bit, I should be going up a little less. Then I should be going up a little less. If I follow the arrows, I should be doing something like that. And if I were to back up, I should be doing something like that. So now you know what happens for any y value between -2 and 0. If you started down here, you just go over more slowly and then come up and then start to taper out, right? What about if you started below -2? And it would get more and more decreasing, right? And the closer I start to -2, the more slow at the beginning it'll be, right? Okay. What about in here? Like that, right? What about above 3? Okay. I've got two different behaviors, my equilibrium solutions. The limit as I go to the right, as t goes off to infinity, depends on which section I'm in, doesn't it? The limit as I go to the left, as t goes to -infinity, depends on which section I'm in. Now you can tell me stable or unstable. For each equilibrium, do I go away from it or do I go towards it? At -2, we're going towards it as we go that way. Yeah, I'm only going, equilibrium is thought of as time goes on. So I think I'm going to the right. Yeah, so that's unstable because we go away from -2. But we go towards 0 and we go away from 3. So I have unstable at 3 and -2. I have stable at 0. It is also possible, by the way, to have the arrows go in the same direction on both sides of an equilibrium. So we'd be approaching from one side and leaving from the other. That's called semi-stable. Didn't happen in this picture, but it is possible.
How about if my graph more than 1 piece?
Well, because I don't have an equation for that, I can't. If I had an equation for f of y, then I could do it exactly the same way. But we don't know what this equation is, do we? We're just given a picture of it. So I have to do this entire thing graphically without having a computational version to fall back on. That's okay. The whole point is that I can go from this graph up here of f of y to the corresponding autonomous slope. And by the way, you don't actually have to put a lot of arrows on here. You could literally put like one arrow in each section. This sort of analysis happens so. What the hell happened? What's going on here, people? Go back there. That's the sums one. I forgot to bring my journal article. I have a journal article on this exact process that says if you actually know the factored version of your polynomial, then you don't actually even have to draw this, you just have to do the sign chart. Because really all I'm saying is positive, negative, positive, negative. Right? Those are my intercepts in my picture. We're positive on this side. Positive means we go that way, to the right. Negative. We're negative in this section, so we go this way. Hey, wait a minute. I'm going away from that spot, aren't I? That must be unstable. Here's this spot between -2 and 0. I'm positive. I'm going this way. That must be stable. Under -2, I'm negative. This must be unstable. All I really did in this picture is turn this one sideways. Excuse me. Better? More questions. (22) So this time we want to use Euler's method, right? Okay. What is the differential equation in question? Y prime equals x squared y minus 1/2 y squared. And they tell me y of 0 equals 1. That's my starting point. How many steps and where am I going? Oh, how big are they? What's the problem say? Where am I supposed to end up? And my step size? Great. So I'm going to do 5 steps, just like I was doing yesterday. Perfect. Okay. The new y value, I use my linear approximation. I take the y where I am, find the slope, multiply the slope by change in x. Change in x is my step size. So I start at 0, 1. My next one, the new y value, is the old y value plus slope times 0.2. How do I find slope? I put the old numbers into this equation. 0 squared times 1 minus 1/2 1 squared. What's my slope? Well, that makes that negative 0.1, right? So now I have an x and a y. I found my next point. Repeat 4 more times. The other thing you can do is you can edit the program we were looking at, in which case I'm going to use t instead of x. And I would write t squared times y minus 0.5 y squared is k. I would suggest doing it this way by hand so that we get a good feel for it. If I'm doing a large process, like I want to do this for, to get from 0 to 1 in 100 steps, I'm not going to do that thing by hand. I crank it out with step size 0.01, throw it in the computer and say go. Better? This process works regardless of the complexity of my differential equation. For any first order differential equation, I can do this. The problem comes when I have higher order differential equations. I can't do this anywhere near as well. Because if I had a second order differential equation, I not only would need to know about y at my given point, I'd need to know about y prime as well. That's harder.
I'm kind of confused on this, how you do that, like the new x.
Because I took one step. I just keep adding 0.2 every step. So my next one will be 0.4 comma whatever I get out. My next one will be 0.6, 0.8, and then 1. You're welcome. I'm always moving over exactly my step size. One 2.5-inch rolling step for lunch. More questions? Oh, okay. Old is the one I just finished finding. So the next one but now it's x squared y minus 1/2 y squared. So I'm using the numbers I just found in the previous part. Frequently, we'll see this written like an iterative procedure. So instead of new and old, I'll write it like I write sequences. Does that make it better or worse? That's our recurrence idea of an plus 1 in terms of an. I will freely admit, one of the things I enjoy most about differential equations is their applicability to almost any situation. We just saw electric circuit work in two different ways, yesterday and today, one of the homework problems. But that same equation is also good for vibrating objects. So it turns out a beam, like just a ruler or something, pinned at one end, has that same sort of motion equation that we were thinking about with our electric behavior. But clearly there's something slowing it down there, right? Air resistance, gravity. So all of those things in physical vibration end up following the same sort of second order differential equation that our spring idea from yesterday's, Monday's discussion followed. And that same expression governs our electrical behavior. It also governs building motion. If I have both ends fixed and I look at the vibration behavior, then I look at the vibration behavior in 2 dimensions. Okay, I want you to imagine it is a lovely, clear, breezy day. Of West Virginia. New River Mountain Gorge. Anybody driven over the bridge? Huge bridge, right? My wife closes her eyes, squeezes them tight, refuses to open them while we're over that bridge. Same sort of situation occurred in Tacoma Narrows in Tacoma, Washington. The bridge going over a river, the Tacoma Narrows Bridge, was just sitting there gently swaying in the breeze. And as the breeze picked up, it started to vibrate more and more, just like the spring on the mass on the end of the spring. But as it started to vibrate up and down, it also started to vibrate back and forth, twisting. Why was it vibrating? Because as the wind blew, the wind shook the cables, which shook the surface of the bridge. Tacoma Narrows Bridge got into an unfortunate resonance occurrence and started to vibrate more and more and more and tore itself apart. The wind was less than 15 miles an hour. This is the same sort of reaction that happens when a singer holds up a glass and sings just the right note to cause the glass to shake. His voice, her voice, is putting energy into the glass until the structure of the glass can't handle it. The exact same procedure. All it took was a breeze. Anybody drive up 30 into North Versailles? You go up 30 into North Versailles, the North Versailles bowling alley, most of the way up there. You can see off to your left one of the steel plants. You're crossing the Westinghouse Bridge. There's a sign on the side of the Westinghouse Bridge that says brake cadence. Because there used to be army regiments moving across that bridge. And if they all marched in perfect step, they might, just might, cause the bridge to start vibrating. Same way that the Tacoma Narrows Bridge vibrates. Oops! So you're not allowed to march across a bridge in cadence. You're officially required to break stride with the people you are marching with. The things you learn when you study differential equations. Questions? Get me back on task or I'll wander off again. Then I wish you all a wonderful weekend. I will see you all on Monday. I will collect this and I will actually start solving these things out analytically. We'll do some actual calculus. This particular one will take a while, but the one we just did, we can do.